Okay, so today we have to talk about curves. Um, my plan was just to start first by showing you a couple of animations because that's an easy way to get like an intuition about how to describe curves mathematically. And then I'll start giving you a couple of some of like the most basic formulas. But here's like how you should think about a curve. So this is like literally like a curve. So you should think about a curve like some sort of like piece of a wire like floating in space. It kind of looks like this. And so for us, like what makes it like one convenient way to think about a curve, if you think about it as some sort of like road that floats in space, is that like a curve, if it's like a road, then you can drive along it. So in a sense, like a curve is like a trajectory of a particle moving in space. So the way you want to think about a curve is that it is a trajectory of a particle. So what that means is that the particle is moving along this curve. So maybe the particle is like here, like if you follow my finger, the particle is moving along the curve. And so at any given time, the particle has to be somewhere, right? So maybe at this time is here, at this other time is here, this other time is here. So what that means is that you want to describe a curve, you want to describe the position of a particle as a function of time. So a curve, again, I'll write more details in a moment, but I do want to show you some animations first. Again, like a curve, it looks like a piece of a wire, something like this. Okay. And the idea is that if you think about the like a particle that moves along this curve, then like there's this dot representing the particle that's moving along the curve. And so at any given time, it has to be somewhere. So the goal when you have a curve, okay, the way to think about this is that the position vector is a function of time. So position of the particle. And then this is a function of time. So for us, describing a curve just means describing this position vector as a function of t. So a curve from this perspective is just like saying what the x coordinate is, what the y coordinate is, and what the z coordinate is as a function of time. Okay, so I'm going to show you first like some animations of how this looks, and then I'll give you some like more like the basic theory. I think not everyone can see this. Let me put it like this for a second. But I still haven't written too much. I just want to show you first some stuff on the computer. Okay, so I think I already used this command on GeoGebra before, which is a command for curves, but it's a very useful one now. Let me show you how to use it because again, it's like a good thing to get acquainted with. So, again, in GeoGebra, you can enter curves. Oops. So there's like these these things that you can enter in the curve command. Expressions here just refer to x, y, and z as functions of time. Okay, so let's start just simple, like the easiest functions of a variable are kind of like linear. So I mean something like where like t is kind of like raised to the power one. So like 2t plus one, then 3t, then maybe t minus one. And then what you have to tell GeoGebra what's the name of the variable. So the name of my variable is t. And again, you have to give some particular values to t. So maybe t goes from -3 to 5, just to say something. Okay. And so these is like the parametric equations of the line, right? X, Y, and Z as functions of t. And here you can see the line, right? So this is kind of like the most basic, like you can think about this as some sort of curve. In fact, I don't know, maybe I shouldn't draw the plane. If I don't draw the plane, like the curve is, the line is more easier to see. So this is kind of like the basic, like the most basic version of a curve, right? Because like the dependence of X, Y, and Z on T is just like linear. And once you have like this prototype of, of the command, then you can just vary a little bit like the expression. So for example, an easy thing you could do is just like maybe raising T to some powers in for some of the entries. So like, for example, I could put, I could put like instead of 3T, let me put 3T squared. And instead of T minus one, let me put T cubed minus one. Okay. And once you have something like that, then the curve changes, how it looks. So if you look, like the point here is like, this is, the way you should think about this is like, this is giving you the coordinates X, Y, and Z of a particle that's moving along the curve as a function of time. Okay. And like the reason why I chose, this like raising T to 2 or 3 is just like to have something concrete, but you can even like, play with like more like interesting expressions. Another thing you could do, for example, is that you could put, instead like another nice function of a single variable is like cosine and sine, right? So you could put cosine of T, you could put cosine of T here. Oops, let's see if I can put it. Try to. Let me, let's just do it again with cosines, because this is another useful one. So you can do, okay, now cosine of T, sine of T, then T, then let's say from -3 to 3. Okay, let me show this one with cosines. Okay, so like, what happens here, this actually is called like a helix. But what happens here is like, cosine and sine are periodic functions of time, right? So like, after a certain amount of time, the X and Y values return to what they were, and T just keeps increasing, right? Like the Z coordinate just keeps increasing over time. So that's why you see kind of like the Z coordinate, like, which is kind of like the height that goes increasing, but like somehow this is become like some sort of a spiral. So that becomes more clear, if you put like some more values here, like let's say -10 to 10. Okay. So if you do it like that, you see like there's kind of like a pattern that repeats itself. And if you look at it from like the top of the Z-axis, it becomes like a circle because X and Y are just like, like rotating basically on the XY plane. So what I'm trying to say is that, like a way to think about a curve is just like, choose your favorite functions of T and just use those at the entries of the coordinates, okay? So in this case, like it was 2T plus 1, 3T squared, T minus 1, but here it was cosine sine, and you could have other things. You could have things with exponentials, you could have other stuff. Does that make sense? So it is any function of time that, you would like to use. They're more like, they're really complicated things that you can represent using curves. So I always like to show this, on Wolfram Alpha. Right, so you can like have, and they're like on Wolfram Alpha, you can put like curves of famous people, and it will give you like equations for like the curve. So, so this is like the equation for the x coordinate of the Einstein curve. Keeps going down, 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 and then that's all of like what you need to represent the x coordinate. And then comes the y coordinate. So that's like the formula for the y coordinate of the Einstein curve. And like you can do it like, it doesn't have to be like the real people. You can put like a center curve also. And then there's like a center curve as well. And so it has like a similar expression. And like, of course, it's like a huge mess, but it's just the important thing here is like, everything depends on T. That's what I'm trying to convey here. So like the expression is like a very complicated function of time. Okay, so that is what is kind of giving you the position. Like what that means is like, if you imagine like moving like along the curve, there's like a formula for like your position as a function of time, and that's like this formula. Okay. Is that making sense? So
Yeah, how's the solution actually generated?
Oh, I mean, like it just uses well, I mean, this is not like maybe like correct a lot of details that I'm giving you, but if you look at this, it's all like in terms of signs, right? So it uses something that's called Fourier analysis, where essentially you can just decompose any function in terms of sines and cosines. So what changes here is like that you use sines of different frequencies, and the point is that by superposition, you kind of approximate anything by sines and cosines. So it's like I mean, again, saying like Fourier analysis maybe doesn't say much, but like that's kind of like the idea that any function, like like any function can be read in an appropriate sense, can be written in terms of sines and cosines. And so, but yeah, like I'm sure like the algorithm itself like has a lot more details that go into it, but like it does like the conceptual most pillar of what's going on is that you use Fourier analysis. But yeah, it's actually kind of fun to just start typing names to see what they generate. But like the important thing here is like it's just a function of t. However complicated, it's just a function of t. Okay, so when we talk about curves, the main idea is to think about them as being given by functions of t. Okay, so that's kind of what I wanted to explain before giving you some details on the board. Is that making sense? Are there any questions about this? So let me go back to the board. So again, to describe, so the point here is that to describe a curve, you need to give x, y, and z as functions of t. You need to give And doing that, I mean, if you describe a curve in this way, that's what we call like giving a parameterization of the curve. When you do this, and when you do this, you say that you have parameterized the curve. So what we'll start talking about in the first half of today is just how to parameterize some basic curves. Like because from there we can just build up and do more like interesting examples. Okay. So let me give you the most important example of all. So here's example 1. And this is the most important example. This is like one that we'll use over and over and over. You'll see how we'll use it tons of times. So I'll think of the curve. In this example, I'll think of the curve as cosine of t, sine of t. And before, like, I mean, some might recognize what this means. Again, this is kind of a formula for like the x coordinate as a function of time and the y coordinate as a function of time. So let's just try to plug in certain values to make this a bit more concrete. And you can think of it as a table. Okay, so for example, what if t equals 0? That's the easiest value that you can plug in here. Okay, so what do you get here? You get cosine of 0, sine of 0, right? And that's 1 comma 0, right? So the way you should think about this is that at time 0, the particle is at 0.1 comma 0. Okay, so let's just draw the 0.10. And that's your position at time 0, okay? So this is t equals 0. Then another, like, just to give a few values, let's do those values where we can evaluate sine and cosine just to make it easier. So if you put like t equals pi over 4, I'm working with radians by the way. So you get cosine of pi over 4, sine of pi over 4. And so what does it give you? Well, it gives you like 1 over root of 2, 1 over root of 2. Right, so that is somewhere in here, maybe. And that's where you are at time pi over 4. Okay, and then just to do like 2 more values, because hopefully you're kind of like seeing where this is going. Like, if you put t equal pi, for example, you get cosine of pi, sine of pi. So that is, negative 1 comma 0. So this is where you are at time pi. And then just one last value to show you how this looks. So 3 pi over 2, if you put 3 pi over 2 here, you get cosine of 3 pi over 2, sine of 3 pi over 2. And that, what does that give you? That gives you 0 comma negative 1, right? So for example, here you have 0 comma negative 1. And that is a position that you had at time 3 pi over 2. That making sense so far so good? How I'm plotting everything. So maybe you can see that you have to imagine that you start plugging these for every possible value of t, right? Not just like these 4 particular values. So just imagine like choosing any possible value of t and you start plugging in. And so the idea is that you will like you kind of imagine something that like a wire or like a curve that passes through all these points, and you will get a circle, right? So these so the curve is going like any point here will be a circle. Why a circle of radius 1? Because so why? Because cosine squared plus sine squared equals 1, right? So what is x of t squared plus y of t squared? That's just cosine square of t plus sine square of t. So that's just 1, right? So that is precisely the equation of a circle of radius 1. So what this is saying is that, if you have the point x of t, y of t here, right? This point satisfies the equation of the unit circle. So it has to be somewhere in there. Does that make sense? So that is why this curve describes the unit circle. And how are you moving along this curve? You're moving counterclockwise, right? If you think about it, because from t equals 0, you first move along the first quadrant. And so this is like a this is describing the unit circle. As time increases, it is describing the unit circle in a counterclockwise fashion. Okay. So this is let me be more specific. So r of t equals. So what I'm trying to say is that r of t equals cosine of t, sine of t. This describes a unit circle in a counterclockwise fashion. circle moving counterclockwise. Okay. And in general, I mean, this is kind of like what we need to know. For now about the circle is that say if you don't have the circle of radius 1, but you just have like a circle of radius r. Right? So what is parameterization of the circle? Or what is a way to give like this circle in terms of t, the equation of the circle in terms of t? Well, it's essentially the thing that I wrote here, but you just have to rescale by r in front of the cosine and the sine because now like the radius is r. So if you write something like this, so now this represents the circle of radius r. So this represents. Any concerns or any questions about this? Again, moving counterclockwise. So again, this is giving you the position of a particle moving on the circle, moving counterclockwise on the circle. As a remark, just for those who are interested, we won't use it, but just I'll just mention it. If you write something like this, so if you write like r cosine of omega t, r sine of omega t, that is kind of still like a circle of radius r, but where the particle is moving at angular velocity omega, if you have seen that. So that is a circle, a particle moving on a circle of radius r with angular velocity. But not something we'll use. We'll think about the circle in this way. But this, like, if you have seen this, like angular velocity stuff, that is how it's related to it. Let me just answer this question. Yeah.
Cosine t over.
Cosine of, you mean like, here, like, oh, you mean like putting the r inside the.
Sine t over.
Oh, so for example, like you can still like, you can plug in some values of t. So for example, what happens if you put t equals 0? Like if you put t equals 0, this would give you the point r comma, it's r times 1 and 0, right? So that would give you like the point r comma 0. But if you divide by r, you would get 1 over r. You know what I mean? You get 1 over r comma 0. So it wouldn't give you like the radius r. Or what were you thinking?
Transform it, be like cosine squared t over r squared plus sine squared over r squared equals 1.
So right, but the thing is like now I don't want this on the unit circle. I do want it on the circle of radius r. So I do want, like, if you think of this as if you think of this as x of t, right? and this is y of t. Now x squared plus y squared is like r squared cosine square of t, right? Plus r squared sine square of t. So that gives me r squared. So that's why it's on the circle of radius r. But that's why like if you divide it by r or something else, then that wouldn't be on the unit. I mean, that would be on a circle of a different radius, but I do want this to be on the circle of radius r. Someone else. Okay, so here's like an application of this idea. Let me show you how to do this. Maybe first, let me show you the animation. That could be helpful. So here's an example of how you're supposed to think about these problems. Let's take the equation of a plane. So let me take something simple like x plus z plus y equals 1. Okay, that gives you a plane, which is what you see there, right? Let's change the color so that it looks better. So I have the plane here. And then I'm going to draw a cylinder as well. So let me draw x squared plus y squared equals 4, for example. Okay. So you have the plane, right, which is a piece of paper, and you have the cylinder, right? And so you see, like they're saying, like the two meet somewhere, like they intersect. Okay, this looks better. So the two intersect, right? So imagine just having like a piece of paper and you like pass like a cylinder through it, right? So there's like an intersection, and that intersection actually looks like a curve. Okay, so what you can try to do is find the equation or the parametrization of that curve. So that's what I'm going to show you how to do next. So is like the picture making sense? So it's like again, like just having like a cylinder pass through a plane, and then you get like some sort of curve. Let me draw it here. So this is a more important example. So, or more like complicated example. So you have the plane x plus y plus z equals 1. So this is a plane. And then you have the cylinder that I just drew for you. So this is a cylinder. X squared plus y squared equals 4. Okay. And the idea is that both, when they intersect, they give you a curve. Okay, so this is the curve of intersection. So the problem is to find the parametrization of this curve of intersection. So find the curve, or like what the problem would say is find a parametrization for the curve which is the intersection of the plane and the cylinder. of the plane, x plus y plus z plus one. And the cylinder. X squared plus y squared equals 4. Okay, so again, what does it mean to parameterize the curve? What that means is that you want to write x, y, and z as functions of t. So that's the goal here. So the goal is to write x, y, z. And by x, y, z, I mean a point of the curve. So just imagine that you have a point on this curve, x, y, z. You have a point on the curve, which is x, y, z, and you want to write that as a function of time, because then that would give you the time and the position of a particle on that curve as a function of time. Okay. So, okay, so if you want to describe x, y, and z as functions of time, there are like two of the three. Two of these three can be described in terms of t with what I have on the board. I don't know if anyone wants to take a guess. Yeah.
X and Y can be two opposed t and two sine t.
Good. So this, like, I mean, I'm thinking about this as a cylinder, but if you think about it, it's also like, I mean, it's really just like the equation of a circle that you move along the z-axis. So if you start with like, so let's start with x squared start with x squared plus y squared equals 4. Okay. If you compare that, that is the same equation that we have here. So if you just look at that, it allows you to write x as r cosine of t and y as r sine of t. So we can write let me use a color, let me put it in yellow. So you can write x as r cosine of t. But what happens to be the radius here? In this case, 2. So this is 2 cosine of t. And y is just r sine of t. So that's 2 sine of t. Is that making sense? Because secretly, I mean, there is like the cylinder is just a bunch of circles. So essentially what this is saying is that the particle, like the XY coordinates, in a sense, like are part of any of these circles, so they have to satisfy the parameterization of the circle. So like you can, and this is kind of something that will happen basically in any of these problems about finding curves. As some like you do have to use eventually this equation. So you will need to use somehow that x squared plus y squared equals r squared means that you can write x as r cosine of t and y as r sine of t. So that's like the problems that you'll be given typically just involve that idea at some point or another. In this case, it was from the very beginning that was clear, but you'll see in the next example that you have to do a little bit of work for getting there. But if you have x and y as functions, if you already have x and y as functions of time, then the only thing that you have to do is like write c as a function of time. Okay, but how can you do that? Well, you can take the plane equation. The plane equation relates the three variables, right? So you can use the plane equation to solve for z. And since you already have x and y in terms of t, that will give you z in terms of t. So how can you do, what can you do to find c as function of time? So to find c in terms of t. So you can say that z equals 1 minus x minus y. So what does that give you? That gives you that z equals 2 cosine of 1 minus 2 cosine of t minus 2 sine of t. Okay, so the parameterization, let me erase this. What is the parameterization? It's r of t, it's cosine of t. Sorry, r of t would be x of t, y of t, sine of t, or c of t. But that becomes 2 cosine of t, 2 sine of t. Okay, so that is this is a parameterization of that curve. This is telling you any point on the curve as a function of time.
Will we ever be given a problem that doesn't involve like this specific thing with the r cosine t, r sine t?
No, all the problems will have that at some point. But you see in the next example, maybe that doesn't appear as the original equation. So you do need to get to that equation, but at some point you will have to use it. So, I mean, there are more complicated things to do, you could do, but like, we'll kind of keep it simple. So that's kind of like the most thing that you have to worry about. But let me plot it first, and then I'll do one of those, so that you can see, what I mean. So. Okay, so we had, again, we had the cylinder, the plane. So the curve, if you wanted to plot the curve, you use the parameterization of the curve. That's what we're doing this. So what was the first entry? It was 2 cosine of t. What is the second entry? 2 sine of t. What is the third entry? 2 minus 1 minus 2 cosine of t minus 2 sine of t. The name of the parameter is t. And let me make the parameter go from 0 to 2 pi, because like, sine and cosine repeat itself after 2 pi, they have period 2 pi. So that's enough to kind of see like the entire curve in this case. You don't, can you see that, can you see the curve here? And that's the parameterization of the curve, okay? So that's how it looks in this case. Does that make sense? Let's do a more complicated example, but it still will use this idea. So, here's another one. Okay, so. So I gave you x squared over 2 plus y squared over 2 plus z squared equals 9. If you ignore the halves, that's essentially the equation of a sphere, right? The fact that they're like these 1/2 like in front of the x squared and y squared, they just like elongate or stretch some of the coordinates, so it's why it ends up looking like what you call like an ellipsoid, but qualitatively it's kind of like a sphere. So you can think about it like as a sphere, just stretch a little bit. So you have that sphere. Let me hide the plane. So you have that, or sorry, you have that ellipsoid, and then you have something like. Okay, so now you have like z, which is the square root of x squared over 2 plus y squared over 2. And if you remember, like the list of figures I gave you last time, that's essentially like the equation of a cone. In any case, the problem would say cone, just to kind of guide you how that's supposed to look. So what I'm doing here is like intersect, I'm intersecting an ellipsoid with a cone, right? So I get like a curve. I get a curve which is hopefully you can see it here, like I'm trying to show it on with the mouse, like you get like this kind of curve. So we're going to try to parameterize the curve of intersection of what you see here of between the cone and the ellipse. Is that making sense? So let's try to do that before, and then I'll switch to a different topic. So we have the ellipsoid, right? So here's the ellipsoid. X squared over 2 plus y squared over 2 plus z squared equals 9. And you have the cone. So you get like an intersection curve, which is here. And you want to parameterize this curve. Okay. And the goal in general, again, for the type of problems you have to worry about, the goal is to try to get to an equation involving x and y. So I'm trying to get x, y. So how can you do that? Well, if you're working, the idea is that you want to work with the intersection, right? So you're working with these two equations simultaneously. So you can just substitute or plug in the equation of the cone into the equation of the ellipsoid. So in this case, you can plug in the cone equation into ellipsoid. So you get x squared over 2 plus y squared over 2 plus z squared, like it becomes equals 9. Okay, so the square roots cancel, right? So you get x squared over 2 plus y squared over 2 plus x squared over 2 plus y squared over 2 equals 9. So So you get x squared plus y squared equals 9. So you see, like, would you end up getting to this like circle equation? It's just that in this case it was hidden in the sense that it wasn't explicitly given to you like as in the previous example where I just gave you the equation of the circle. Now you have to do a little bit of algebra, nothing too like too crazy, but you did need to use some algebra to get there. Okay. And once you get there, like you say, okay, this is like a circle of radius 3, and so that immediately allows you to say x equals r cosine of t, y equals r sine of t. So this is 3 cosine of t, and y is r sine of t, which is 3 sine of t. So far, so good. And what is z? For z, you can use any of these two equations because the intersection is supposed to satisfy both at the same time. So you can plug in x and y in any of in your favorite equation. In this case, it's easier to plug it into the cone because like the cone is already solved for z, right? So it's easier just to plug these two into the cone. So when you plug x and y into the cone equation, and then what do you get? You get z equals x squared over 2. But what is x squared? That's 9 cosine square of t over 2, right? Plus y squared over 2, that's 9 sine square of t over 2. And that's just, you need to substitute, get the 9/2 out. So you get cosine square of t plus sine square of t. And cosine square plus sine square gives you 1. That's like an identity you will have to use tons of times for these type of problems. So these just like root of 9 over 2. Which if you, there are different ways to write this if you wanted for some silly reason. Like you could write it as c equals root of 3 over root of 2, for example. So that means that the height is kind of the same value throughout the entire curve, which is kind of plausible from the picture, right? So that means that this curve of intersection, which is actually like some sort of circle, doesn't change its height, like it's completely parallel to the xy plane. So the circle of intersection is not tilted. That's what I'm trying to say. Which you could have said, like kind of seen from the geometric picture, but like the algebra kind of like verifies that. So the z is actually independent of time, but the parametrization. What is a parametrization? The parametrization is just r of t equals x of t, y of t, of t. Sorry, I don't know why I keep saying sine of t, z of t. But we know that x of t is just 3 cosine of t. Y of t is 3 sine of t. And then z of t is just 3 over root of 2. So again, if, I won't do it again for this one, but you can go to GeoGebra and use this curve command. If you enter the curve command with these entries, you will get that intersection on the picture. Yeah.
Well, so when answering these types of questions, do you hear like where he starts? Because like for example, if you could switch it could be 3 sine of t, it could be 3 cosine of t, then 3 over root 2, and it would be the same curve, it's just he would start.
Right. So for this, for now, I'm not too particularly interested in specifying the t-values. There will only be a small part of this topic where we do care about that, where it's when you find the length of the curve. But until then, like, like for example, someone could say, oh, the t goes from 0 to 2 pi. That's kind of like the minimal amount that you need if you want to cover the entire curve. But if someone say like the t goes from negative infinity to infinity, that's still the same curve. It just means that you went over like, each of the points on the curve like infinitely many times. So it's kind of like a particle that's just like spinning around the circle over and over and over and over. So it's not super important as of now, what the range for t is, until we talk about the length of the curve. but yeah, so for now, like, just like the formula is what I care about, but yeah, that's a fair point. Like you, depending on how you parameterize it, then like the t-values could be different, but, you could also use negative t's, or like, you could also have said like this is actually goes from minus pi to pi, for example, that also gives you the same curve. So there's some like redundancy sometimes in all these formulas for the curve, because it can be described in different ways. But we just kind of like, for practical things, it's more like the really important thing that you have to know is like the parameterization, like the actual formula, and then like, yeah, you can think about what what the t-value should be, but it's not super crucial at this moment to kind of decide on that. If that makes sense. But that's good. Anyone else? Okay, so again, like this is like just like example of how you can use this idea that x squared plus y squared equals r squared in terms to write x and y in terms of cosines. You can apply it in different situations to get like more interesting curves. But hopefully this shows you the important part of what I have been saying, that is just that a curve is something where x, y, and z are just functions of time. Once you are convinced of that, then you can do a little bit of calculus. So let's just think about that for a second. Now, let's say you have a curve. I'll try to draw the curve again, like a piece of wire. So try, you have a curve like kind of maybe looks like this. Okay, some sort of road in space, like particles moving along that road. So maybe. Okay, let's see. So maybe this is like the position of the particle at time t, right? And kind of like similar to any thing about calculus, you move after time t, you move an amount, or let time go by an amount delta t. Okay, so now this is going to be the position of the particle at time t plus delta t. Okay, so do you think of delta t as being super small? And then if there's like a vector that connects these 2 points, right? Right, there's this vector that connects these 2 points. I'm going to call it delta r. So it's like a change in position vector. Right? If you think about delta r, like, if this is like the point P and this is the point Q, it's kind of like the vector that goes from P to Q that we have talked about before. So delta r is just like, think about this as like change in position vector. Oh. So this is just r of t plus delta t, right? Minus r of t. It's so far so good. And then if you divide this by delta t, that's the average velocity for the particle from time t to time t plus delta t. So what is delta r over delta t? Oh. So this will be the average velocity of the particle that it has from this time to this other time. This is the average velocity. Right? And then as delta t goes to 0, like the limit, that is what you would call the instantaneous velocity, right? Like, so the limit as delta t goes to 0 of delta r over delta t That is just the like actual velocity or the instantaneous velocity. Which okay, I'll call it in two different ways, but for now, it makes sense, if you follow the calculus notation, I'll call it the RDT. So this is going to be called DR. Not making sense. Uh, And the good thing is that you would say, okay, now you have to relearn calculus, and not really, it is just doing calc one again, but 3 times, because you can do it for every of the coordinates. So the point, and this is the nice thing, so far that, so if you think of R of t, you know, if you think of R of t as x of t, y of t, and z of t, right, that can also be written in terms of ij and k as x of t I plus y of tj plus z of tk. The thing is, like, ij and k are kind of like constant vectors. So essentially, to know how this position vector is changing with respect to time, you only need to understand how x of t, y of t, and z of t are changing with respect to time. So if you were to follow all the steps in this limit definition, which I won't do, what you end up finding is that this thing that I'm calling the RDT is just what you get by taking the derivative of each of the components individually with respect to t. So the RDT, that's the nice thing about this formula, is just the XCT I, like, let me use a different color for I, J, and K to distinguish it. dy dt J plus dc. Meaning that to take a derivative with respect to time, you just take each of the coordinate, like the regular calc1 derivatives of each of the coordinates. So this is like, or if you prefer to write it this way, this is the same as exdt dydt. So to take the derivative of a curve with respect to time, to take the derivative. You take the derivatives of the individual coordinates, or you take the derivatives of each coordinate. Okay. Okay. So let me give you an example, then I'll tell you what this vector gives you. So let me just erase this quickly. So you may remember the example that we were doing last time, right? Like where you had actually the first one, you had the plane. It's an example. You had this plane, you had the cylinder radius 2, I believe, right? And the curve, right, we had found before that the curve had parametrization to cosine of t, to sine of t, and then 1 minus 2 cosine of t, minus 2 sine of t. right? So I'm saying if you wanted to take the derivative of this with this parameterization with respect to t, it's just like the derivative of each of the individual entry. So what is the RDT? The easiest thing you could try. So the derivative of cosine is minus sine, right? So you get -2 sine of t. The derivative of sine is cosine, right? So you get 2 cosine of t. And then, okay, the derivative of a constant is 0, right? So minus, okay, there's a cosine which is minus sine, becomes a plus. So you get 2 sine of t minus 2 cosine of t. So that's what I get if you just take like the ordinary calc 1 derivatives of each of the coordinates. Is that making sense? Now, what does that give you? This is a vector, right? You know, it's like in a sense like the first derivative, right? So in calc 1, like first derivative was related to, you know, like slope of the tangent line. So there's like a tangent line involved. This is kind of like the vector version of the slope. This is just like the direction of the tangent line to the curve. So what this is saying is that this curve, let me draw the curve because I forgot to draw it. So you had like the curve of intersection and at a point on the curve, there's like a tangent line. I'll write this again in outside this example. So you have this tangent line and the line has a direction. We already talked about this, right? So the line has a direction V and that direction V is the RDT. Okay, so this line. Okay, so like let me draw write this again like in general. So what I'm saying is that when you have a curve, when you have a curve, when you have a curve, there are tangent lines to this curve. Right, so here's, for example, a tangent line. This is a tangent line. And as a tangent line, it requires a direction, right? And the direction, which is what we usually call the vector V. The direction, which is vector V, happens to be the RDT. So this is just the RDT. So the RDT is a vector which gives the direction of the tangent line. Is that making sense? So this also coincides with what you call the velocity vector of the particle, right? So if you think of a particle moving in time, the RDT vector is the velocity of that particle as well. But for now, like we're thinking about it as you know, as being like the vector that gives you the direction for the tangent lines. Okay, so I can maybe to finish today, let me do an example about this. Are there any questions so far? So this part is like the trickiest part of this section is actually just finding the equations of the curves. The rest is kind of like doing calc one to the curve, applying calc one to the curve. So you see, you'll see like today we were doing like the derivatives. Next time I'll tell you how to integrate that if you say, and besides that, integrating or taking derivatives, there's not much else to do. But like it's still calc one that we're doing is that we're just doing it 3 times because now everything has 3 entries. Well, just to finish this up, okay, let's consider the helix. Consider the helix. So you don't need to know how that looks, but it looks something like this. It is one of the first ones I show you on your algebra today. So it's kind of like this spiral. So that's what the helix looks like. So let's say the point P, let me put the point P here. Belongs to this helix. Okay, find the equations of the tangent line. It's tangent line. Um, find the equations of the tangent line, find the equations of the tangent line to this curve at the point P. From the tangent line to the curve at point P. Okay. So what I'm trying to say is that there's a tangent line to the curve that passes through this point. It looks something like this. Oops. Oh, looks something like this, and we're trying to find the equations of that line. Remember that for a line, we need a point and a direction. Yeah. Oh my God, did I do something? Oh, you're right, because time is pi over 2. So good catch. I you have turned it around. Sorry about that. Right, because cosine, I mean, what's happening here is that t is pi over 2, just by comparison, right? So if you do cosine of pi over 2, you get 0, and if you do sine of pi over 2, you get 1, right? So that's what was what went wrong with my picture or with my point. So the idea is like a line requires 2 pieces of data, right? It requires a point. You're already being given the point. The point is the point P, right? Which is typically what we would call P naught before. And then you need a direction. So what's going to be the direction? It's just going to be the derivative of this curve at time pi over 2, because that's the time that you pass through this point. Okay, so let me write that down to finish this. So for the line, right, for line, we need point plus direction. We need point plus direction. So the point is just the point P. Point is P equals 0, 1 pi over 2. Pi over 2. Okay. And then direction. Okay. So what is the direction? The direction is the RDT What is the RDT in this problem? That's minus sine of t, cosine of t, comma 1. The thing is that gives you the direction, or that gives you the velocity, if you want to think in terms of velocity, at any point on the helix. You don't want the velocity at any random point on the helix. You just want the velocity at this particular point, right? Because that's where you're trying to find the tangent line. So you just have to evaluate this at the time at which you pass through P. Okay, so you cannot leave the answer in terms of T because you want the specific velocity at time P, when you are at time P. So you have to evaluate this at the time that you pass through P. You pass through P. Is that making sense? So that's like the only tricky part of this problem is that you cannot leave the answer in terms of T because you just want the specific tangent line. So the velocity vector would be the RDT at what time? At time pi over 2, because like you see T is pi over T matches the third entry. So this is T equals pi over 2. So when you evaluate this at pi over 2, you get what? You get negative 1, 0, 1. Okay, so the direction, the velocity vector at that particular point is just the vector negative 1, 0, 1. And we have point, we have vector, and the equation of the line. Oops. Gotta get it with this up. I'm almost done. The equation of the line. Which page? Because it's so strange. Turning it out. But like, how can I turn this up? It's okay, fine. So the equation of the line. Remember, is point plus t times vector. Okay, yeah, really frustrating, but I'm almost done. So I'll try to turn this off again. I don't know why this. Let's try to turn it off. So sorry, let me just finish writing this because it's the last thing I need to write. So it's just 0, 1, pi over 2. Okay, probably it doesn't. This is so I honestly don't know what's wrong with this. Well, that was the last thing I wanted to write for today anyways, but this is like the equation of the line. Remember, point plus t times the vector. Point is 0, 1 pi over 2 plus t times the direction, which is negative 1, 0. Is that making sense? Yeah, I will try to find out how can I control this for a better next time. Is there any questions before we finish? Okay, so the only thing is that on Wednesday, unfortunately, I won't be in the country, so I'll do the class from Zoom. I'll record it and everything. It won't be. The thing is that it will be only on things. If there's like a few things left from this topic, they're very easy, so it will be mostly examples. There's not really much theory that I will cover. I'll still record it, but obviously I understand not everyone can show up, maybe because if it's on Zoom, like you have other. So I'll record it and I'll post it. But and also I'll tell you what videos you can watch if you like, from my previous classes if you prefer to watch that. But I'll send out a reminder to everyone. But yeah, so that will be the only time this semester that I have to do that. But I'll let you know. I'll send you the link for WhatsApp. So let me just send the